My name is Tusheng Zhang from the University of Manchester, and he's going to speak about invariant measures for SPDEs with two reflecting walls.
Okay, first of all, I thank the organizers for the invitation, and this is also the work I talked with continuation of the work I talked here 2 years ago. Okay. So we will consider stochastic partial differential equations with two reflecting walls, okay, with constraints. We will discuss the existence of uniqueness of invariant measures, and also recently we established a large deviation principle for this family of invariant measures. Okay, so first of all, let me show you the equation. So this is a stochastic reaction equation if with this constraint. Okay, so we are going to solve this equation with the constraint that the solution always stay within the two walls. Okay. So we use Q to denote this product space, and W is a space-time white noise, and these two terms is also a part of the solution. So this eta and also cassette, these two are also random measures to prevent the solution from leaving the wall. Okay. So for the wall, we assume that of course one wall is smaller than the other. But this should be k. Okay, k. Sorry. So the wall also has distributional derivatives, and we assume the coefficient satisfies the Euro-Lipschitz condition, and also we need this non-degeneracy for the uniqueness of the invariant measures. But for the existence, we do not need the F2. But for the large deviation, we also need more, actually more assumptions. First, let me define the solution. Precisely solution. So a triplet is a solution to the SPDE 1. So if U is a continuous adapted random field, so we look for continuous random. It's not in L2 space. I mean, it's in L2 space, but we are looking for the continuous random field. And UXT is FT measurable. And also UXT is stay within this two walls. Okay, so eta and cassette, this is our positive random measures which are adapted. Okay, and condition 3 says that the solution satisfies the random field satisfies the equation in the weak sense of PDE. It's a weak solution in the PDE sense. So which means that if we take a test function, so then this equation is satisfied. And number 4 says that the extra force we add is our minimal. So this means that the force only acts when the solution hits the boundary. Let me give some words about the history of this equation. SPDEs with one reflecting barrier at 0 was first studied by Niolat-Bardoux when the noise is additive. So they prove there is a unique solution for the additive case. And when the noise is multiplicative, and Donati Martin and also Pardue, they prove that there exists a minimal solution. The uniqueness was left out there. But in an article about 2 years ago, one of my students, Xu, and myself proved that actually the solution is unique. So there is a unique solution to the SPDEs with reflection. Okay, so we use a different approach. So we also established a large deviation principle for the solution. And some also very interesting properties were obtained by Zampotti for this SPDs reflected at 0. And for the SPDEs with 2 reflecting walls, the existence or uniqueness was established by Yang and myself. Okay, now the SPDEs with reflection are the extension of the deterministic parabolic obstacle problem. The deterministic parabolic obstacle problems are often the equations for the value function of optimal stopping problems. Okay, and also it's also proved by Funaki that also Ola that the fluctuation of the delta fair interface model near a hard wall converges in law to the stationary solution of SPD with reflection. So today I want to present the existence of uniqueness of invariant measures and also present a large deviation principle for the invariant measures. For the invariant measures, there are many people working on this subject, but I only mention the ones who worked on the equation which are closely related to this equation. So there are many names in this room I have not mentioned. So this is not a complete list. And for example, I mean Pesat, Zapchik, and also the Prato, Müller, and for SPDs with reflection, when the noise is additive, then the existence uniqueness of the invariant measures was obtained by Otobe. Okay, and also strong Fellow property was also obtained for this equation for the SPD with reflection. So for large deviations for invariant measures of solutions of SPDEs, there are not many works, not many articles. There are, as far as I know, there are two papers. One was given by Sauer, another is by Sarah and Michael Rockner. Okay. So for the large deviations, we will the approach will be along the same line as these 2 papers, and because of we have these 2 extra terms, we need to get some uniform estimates for the approximating equations. Okay. To introduce the result, we first present to you a deterministic obstacle problem, because this we will use at several places. I write down this equation. I will refer to this equation several times. So these are also measures, not really functions. So this is just a form. Now, the wall. So giving a continuous function v, so we are looking for a deterministic solution of this parabolic problem. So here V is given for any V. So we consider this this PDEs with two reflecting walls. Okay. So the result is in the one barrier case it was given by Niolat Pardue, and also the two wall case is given by Tobe. It says that this equation, given any continuous function, random field, this equation has a unique solution. And moreover, if you replace V by another continuous function, then this continuity result, this control holds. This is very important. So if you are familiar with the Square-Hot problem for the ordinary stochastic differential equations with reflection, you also have a similar result. So you can think of this as a Square-Hot problem for in the PDE case. Okay, so yeah, the point is here we only have a continuous function and not smooth. If V is smooth, this was already known in the PDE literature. Okay, now first the existence of invariant measure. Because there is a unique solution, so this gives us a Markov process. We have a semigroup. So now suppose we have the wall satisfies H1, H2, and also we have the Euro-Lipschitz condition. So then we can show that there is an invariant measure. Okay. So I will briefly go through the proof. So I will use the powerful criteria, the Krylov-Bogoliubov theorem. The point is to find the compact set to prove that this transition probability is tight. To do that, I need to find a compact set such that this is arbitrarily large. I mean, it's 1 minus epsilon for any given epsilon. Because of this singular reflection, it's not easy to directly find a compact set, but I will do it indirectly. I will find this K indirectly. Okay. So we need to find a compact for any given epsilon. We need to find a compact set such that this transition probability holds. So what we do, we introduce a continuous random field. So this is a random field. Solve a SPDE without reflection with a given coefficient. U is given. U are the solutions of our SPDE with reflection. So if we consider the difference U, then subtracted by this, this is the heat kernel corresponding to the Laplacian operator. Then if we call this U bar, then we see that then the very important observation is that U bar satisfies a random obstacle problem with random coefficient. Replace V by this random field. So by using the result for the deterministic parabolic problem, then we can claim that the solution of for our SPDEs with reflection is a continuous functional of V. So therefore, to find a compact set, we only need to find a compact set for V, for Vg, which is independent of G. So we need only to prove this Vg is tight, or G. So that is possible because there is no singular term anymore. But this is a continuous function of this V. If we can find the complex set here, then the image of the complex set will be the complex set that we want. Okay. So that's the idea. So then we can get to the existence. Uniqueness is it's harder because the Euro means the method often used in literature is to prove that the semigroup is from Feller, which we have, and also want to prove the irreducibility of the process. But that one, this irreducibility we could not prove. But instead of proving the irreducibility, we use a coupling method to prove the uniqueness. So this coupling method for SPDs without reflection was used by Müller, by Carl Müller. So to use the coupling method, we could not directly use the coupling method for the reflected SPDEs. But we use it for the approximating equations. We prove a kind of uniform coupling. Okay? So therefore, we need this approximating equations. This is the penalized SPDEs. You see, you have you add a fourth. So then it turns out that when epsilon delta tends to 0, then this approximating equations approximates to the SPDs with reflection. Okay, so if we have non-degeneracy for the diffusion coefficient, then we have a unique invariant measure. Okay, so let me briefly go through the proof. We want to construct a coupling, a coupled process, which if we are given two different initial starting points, want to show that the two solutions eventually will meet. So to do that, so we will first consider solutions of this the following two SPDs with reflection. You see, U has the same law as our previous U, and V also has the same law because this is also a space-time white noise, although it's coupled. So therefore, this UV is a coupling of our original UV. Okay, so V has the same law as our U with initial point, with initial value U2. But you see, here this is not Lipschitz. The coefficient is not Lipschitz, so the existence is not automatic. It's not immediate. So we need to construct the solution of this system of SPDs with reflection, and the construction also helps us to prove the successful coupling. So what we do is to approximate the function by Lipschitz function, and we so eventually we can prove that this system, these two SPDs with reflection, indeed has a weak solution. Okay, that's enough for us. We are only considering the law. To prove the successful coupling, we consider this function ut. Yeah, so ut is remember u is a solution of SPD with initial value u1. V is a solution of SPD with reflection with initial value u2. So we want to show that these two will meet. So it's enough to show that u, this capital U, will hit 0. Okay, because we know that u1 is bigger than v. But u is bigger than, because we assume the initial condition u1 is bigger than u2. So we can do that. We do not have a Ito's formula. And also, we will have two random measures here. So we have to appeal to the approximating, to the penalized SPDE. So by several layer of approximation, we can show that this real valued process ut can be decomposed as a martingale part, which is nice, actually very nice. Although it's a martingale, and has another term a. A is a non-decreasing, non-increasing process, but we do not have an explicit expression for A. But we know A is decreasing, so that's this is very helpful for us. And by a time change, we can show that after a time change, then yt is a time change of v of u, and also square root of the time change. So then we can show that yt is given by this equation. It's important to realize that a tilde is decreasing, so therefore this is a negative. So this is negative, this is also negative. So we have this comparison. So by the property of the Brownian motion, we know that the yt will hit 0. So we have a successful coupling, then we get a uniqueness. Okay, let's now move to the large deviation. So we consider the system, a family of SPDEs with reflection, so with a small parameter here. So we know now that for each epsilon, there is a unique invariant measure. So we want to prove that this family of invariant measures satisfies the large deviation principle. Okay, now so to study the large deviation, we need to consider the so-called skeleton equation. Okay, that's very natural. So if you're familiar with large deviation, so this is a Cameron-Martin space for the space-time white noise. So we consider the skeleton equation. Now, in the skeleton equation, you replace the white noise by this smooth function, by an element in the Cameron-Martin space. So we need several estimates, a priori estimates for this, for the solution. So the first one is we need a uniform control for the measure, because the two extra term cause trouble. So we get a uniform control. So we have this. The right side is independent of t. So this is
what's the dot mean?
Dot, because in this case, if h is smooth, then these two measures are actually absolutely continuous. This is the density. It dot is the density of this measure with respect to Lebesgue measure.
Ah, so that's the density.
Yeah.
Okay.
So in this case, the density exists. Yeah. So in general, it's not absolutely continuous. Okay. And we also need to give a harder, give an estimate for the harder norm. This is also important in the proof for the proof. This is an intermediate step. Okay, now we need to introduce the rate function for the family of for the large deviation. Now, suppose given any continuous function, so this is a rate function now for the large deviation for the for u epsilon, not for the invariant measure, but this is for the this is a rate function for the large deviation on the path space for the solution. So this is given any v. So this is a Euro rate function now. Now this is a state space of our solution. So the invariant measure will be a measure on this space. Okay, so this is a complete metric space. So we'll introduce a functional from this space to the positive line, which will serve as a root functional. Okay, so that is our JZ. So given any element in E, so JZ is this all the possible V such that the V starts from 0 end up at point Z. So the smallest energy you can see. Okay. So this is a root functional, and we also have the useful the following useful characterization of the root functional. These are not easy to prove actually. So it's easy to write down. So the first result we prove, this is a family of mu epsilon is a family of the. Okay, now mu epsilon is the invariant measure corresponding to this equation. Okay, so we first prove that this family is exponentially tight. Okay, because we want to reduce the proof of the large division to the large division on the path space. We want to use the large division on the path space. We need a large division on the path space to hold uniformly with respect to the initial condition. So if we restrict the initial condition to a compact set, so therefore we need this exponential tightness. To prove the exponential tightness, so we use the invariance of the measure. Okay, given any set by the invariance measure, so this equation holds. So therefore, it's enough to show that the solution has exponential tightness. So again, this is possible due to the fact that u epsilon is a continuous function of v epsilon. V epsilon which does not have any singularity. So I will suppose we have this v epsilon. So then u epsilon is a solution of this random obstacle problem with v replaced by v epsilon. But for this v epsilon g, we have the tightness. So the same trick as before. Okay. Now I can state the precise result of the large deviation. We assume that the drift is Lipschitz, but with a small Lipschitz constant. Okay, in something is stable. So to get the large deviation. So on these conditions, we can prove that the following large deviation holds. So to prove the large deviation, we need to prove the upper bound and also the lower bound. Okay, so so the large deviation says that for any.
Why do you have this condition if you are, if you have bounded obstacles? Why do you have a condition on the Lipschitz?
Yeah, at some stage we need this. We need a solution to converge it to 0 somehow. Yeah, we need this is in the proof. Yeah, bounded is not a. This is a technical point. Maybe, I will tell you why maybe later in the proof. Okay. So this is the upper bound, which means for any closed set, we have this upper bound, and also we have this lower bound. This is for open set, open subset. So let me go through the lower bound, for example, to see, give you a flavor how we prove this. So it's enough to show that for any given point with finite, such that the value of the function is finite, this exponential inequality holds. It's enough to show this. Okay. To show this, we need to use the invariance of the measure and also the light deviation principle for u epsilon on the path space. So we fix any point with finite, such that the value of the root function is finite by definition of the root function. So that means we can find a constant t0 and a path. The path is given by some is a solution of the skeleton equation with some smooth function h, such that the energy of the h is less than j z star plus this small constant for any given constant. So this just comes from the definition of the root function. Okay. Now we have this function of v. Now the problem is we need to construct a path, a deterministic path, such that for any starting point z, we need to construct a deterministic path so that this path is close to u epsilon, and also this path has the value of the root function for the path on the path space. If we evaluate that root function on this path, is also small. Okay, so you have how to say. So we have a path and to set t0 is z star. So this is nice, but we need to construct a path which starts from any initial point, and also such that at some point this path will be at z star, and also the energy of this path is also comparable to the energy of c. So therefore, if you start from any initial point, so we need that this path will go to 0. At least it will be close to 0. So then we can patch them together to get a. That's why we need this smaller. We need this small Lipschitz constant. Okay. So as I said, we can show that for any initial point, so we can find a solution of the skeleton equation, such that this is for any given delta, this is true. But for this, we need two lambdas actually, because we need this property. So because that's why we impose this condition. Okay, now for the lower bound, again we use the invariance of the measure, because this holds for any t. Mu epsilon is the invariant measure of u epsilon. So therefore, in particular, it holds for this at this point. Because our construction of this solution of this skeleton equation, so this is bigger than this term. So now I can use the like deviation result for u epsilon, which is known, already known. Okay. So, but we need to use that uniformly with respect to the initial point, but we know that the light deviation principle holds on the path space uniformly with respect to the initial point, which are in a complex set. Okay, so by the uniform light division principle, satisfied by U epsilon, this is known already proved. So therefore, we have this. This inequality holds for all initial points Z, which is in a complex set K. So therefore, we can get the lower bound. For the upper bound, it's a similar idea. Is to reduce it to a light deviation principle of U epsilon on the path space. Okay. Yeah, that's it. So, but I will show you some reference. I can save 5 to 10 minutes. So this is the first reference I mentioned. This is a paper I referred. Sauer. And this is a Terra and Rockner's paper and the Funak's paper. And finally, and not yet, finally I want to use this opportunity to do this little advert. So we have an open position in probability, and if anyone is interested, please talk to me, and with good salary, you see, up to 45. Okay, thank you.
Thank you very much. Are there any questions? Did you ever try to think about sticky boundary conditions for SPDs rather than reflecting boundary conditions?
No. Yes, for the ordinary SD, I mean, there is sticky boundary.
Yeah.
So
and
it
so
makes sense.
for SPDs, there should be a kind of sticky boundary condition as well.
So you allow the SPD stay on the boundary for some time, maybe, isn't it? Sticky. Well, that's an interesting question. I'm not.
Looks to me like your condition would be for the deterministic PDE that you have a unique kind of omega, limit point. But I mean, of course, you can also work in principle when you relax this condition, which you mentioned, which we were discussing about. You still have, of course, limit points, but I mean, there can be
maybe several.
Yeah, there can be many.
Yeah.
Is this? I mean, you explained a little bit the technical problem, but do you think it cannot be done?
At this moment, it's just technical. It's just the method proof. It's not maybe not essential. Should not. Why it should be? I mean, why do we need a stable condition? This implies the solution tends to zero.
I mean, why do you need it? I mean, at least in the variational case, I mean, one would expect everything is more or less like in the smooth case, right?
Well, this is just a technical point. Maybe it can be released.
In the case of one constant reflecting barrier, I sort of remember that Zambotzi identified the stationary distribution.
Yeah.
That with two constant barriers?
Yeah. If the noise is additive, then in that case you can write down the explicitly of the invariant measure, which is the law of 3D Bessel process.
That's for one barrier.
Brownian motion condition to stay inside. And so the sticky boundary condition should correspond to reflected Brownian motions.
The sticky.
Yeah. So if you want the SPD so that the invariant measure is the law of reflected Brownian motion rather than the law of conditioned Brownian motion. Then it has to spend more time near the boundary. So it will have to be some kind of sticky.
We heard this talk by Laurent Denis in Lausanne.
Mm-hmm.
And so also did a lot of work about the obstacle problem and so in a very general, quite general framework.
Yeah.
What is the relation? Can you explain a little bit the relation of this area?
You mean the stochastic case? Or?
Yeah, the stochastic case. I did it for stochastic.
Yes, but in the literature they did some, because in that case they only use a framework of the Gafford triple, and this is and also the noise not a space-time. You use Euler's formula.
But also here you can do space-time only in one dimension.
Yeah, that's right.
What one dimension is maybe not so interesting.
No, one space-time is in one dimension. Yeah. So if you use the general result, you need Hilbert, space structure and Euler's formula and so on.
But I think there must be a relation. No?
It's different type. It's a different type of equation.
Sorry, is it?
It's a different type of equation which requires different method to treat. And also, this is related to the talk by Xiang Chen, I think, because but in that case you have additive noise and but it's different type of equation. But we cannot fit this exactly in the framework. Yeah.
Can something be done in the planar domain?
I had one paper, but I have a system of n equations, but I needed the domain is convex, and also I needed the initial condition is nice.
That's for the target, but for the domain of the spatial domain.
Spatial. No. We're only one dimension. The target, the target we can consider system. That's possible. System of reflected system, which have a vector value solution, which stays in a convex domain.
And what is the problem for the more high dimensional domain?
Because like the reaction equation without a reflection does not exist, because space-time wide noise.
Oh, what if there was some correlation?
Oh, that's possible. Yeah, correlation. If you have correlation, that's possible.
Non-convex, you can't do anything for the system, right?
Sorry.
But if it's non-convex, you cannot work with the system. That would be a complete.
At least I needed the convex very much.
Oh,
yeah.
yeah.
I like it. Yeah.
Okay, so if there are no more questions, let's thank Tusheng again.